Okay. Funny part, it wasn't even that big of an order. Okay, so these again are the abbreviations for your amino acids. And again, this is the sort of thing you need to flip card, and you need to have those so you understand them. If you're going to be doing the MCAT, you need to know these just breathing them out. Okay? Like you should be able to wake up in the middle of the night and you should be able to flip card these without any mistakes. Sort of stuff, okay? Like if you were walking down the hall and I went alanine, you should just be able to, structure is this, 3-letter, 1-letter, bam. Is it hydrophobic? Is it hydrophilic? All that off the top of your head, and I should just be able to anytime, shock, surprise, boom, you got it. Okay? That's the level you need for the MCAT because it's an 8-hour exam. If you spend actual resources in your head trying to do questions like these, you will have nothing left for the hard stuff. Okay? If you're going more like a PA school sort of thing, dental, graduate school, none of those have that level of testing, okay? You just need to be able to figure them out. And the level I would do is I'd actually get it so I remember them well enough that at the beginning of a test, I could take scrap paper and I can just write them out. And then I don't actually have to remember them anymore. Does that make sense? Okay. Okay. No problem. Okay, so what is the 1-letter abbreviation for the amino acids shown below? Anybody start their flip cards yet? What the hell? Didn't we clearly express those should have been started like 2 days ago? You guys are gonna really regret it if you don't start them like now. Okay? Really, I mean truly. Start those flip cards. Do them in between classes. Go to the bathroom, do them while you're going to the bathroom. Okay? Get a drink, flip card. Okay? Seriously. And you're gonna have have you guys seen my instructions for doing flip cards? Or have I talked about that? Okay, so your flip cards should be like, if you're doing physical flip cards, which are actually work better than the digital one, and it would be a ring. You'd have a ring. You get the ones that can be put on a ring. And what you would do is you would flip the flip cards. If you do it successfully, you would put a mark on the edge. And you'd keep putting marks on them. And when you do a flip cards 5 times, you can then take it out. Now, what I mean 5 times is forwards and backwards. You should always do flip cards forwards and backwards. And then what you would do is you'd take out old ones that you're getting right, you'd put them in another ring, and they're your, I know these now, and I will do them one more time before the test to see if I remembered them. And then you should add new flip cards throughout the semester. For example, we'll have sugars that we need to memorize. You need to memorize the bases for the DNA. You need to memorize the DNA and RNA structures. There's a lot of information you're going to have to memorize. I know this is the memorization chemistry course. Okay? Most chemistry courses you need to memorize very little, right? Now, it does help that about 60 to 70% of the terms are chemistry terms, and so they mean exactly what they mean, right? Like, they say what they mean, that's it. Unfortunately, we are biochemistry. Those fucking biologists have gotten in this damn subject and name shit after themselves, okay? Which is a no-no. Bad. Sadly, the glassware also has people naming things after themselves, which is, again, ridiculous. But anyways, flip card. If you do the digital ones, the digital one can kind of take care of that organization for you and do that automatically, which is the convenience of it, right? Okay, so anyways, W, N, R, E, okay? Flip card, get that. I'm really, really serious. Like you on the exams, when we hit the exams, if you haven't been flip carding these things and you don't hit the ground running on this subject, you're really going to regret it. It's a 5 credit hour course. You kind of take 2 weeks off. It's like taking a month off for a normal course, right? It's also an advanced 400 level course. It's a pretty bad idea, right? So, yeah. Like if you take the first week off, it'd be like taking the first 2 weeks of the ARGIC courses off, right? Yeah. Okay, so the utility. The reason that these particular 20 amino acids became the protein alphabet is actually not known. We really have no idea. We actually can synthesize alternative amino acids. They actually can work to get incorporated into proteins. And there really isn't a good reason why these 20 amino acids are it. Okay? There's even indicators that there might have been more amino acids at one point, 22. I don't know. Maybe that could be your future careers. Okay? Somebody can answer that. You can come back and go, Dr. Clausen, this is why. Okay? So the possible reasons, though, some of the hypotheses that have been put forward, though I struggled to say hypotheses, informal theories, because they're very complicated to test, and I'm not sure if you can test some of these. The amino acids provide chemical versatility. So these are like the minimum viable set to give you the full chemical versatility you would need. Okay? And so there isn't a major driving force to make more of them because you have all the versatility you need. And then if you shrink that, you wouldn't have all the versatility you need. Sort of middle ground, right? The amino acids may have been available from prebiotic reactions. So it could be components of them or it could be the whole structure, the side chain, is something from something else. And that's how evolution always works, right? Why are human eyes designed the way they are, even though they're actually a terrible design? Octopi have far superior eyes. Shrimp have far superior eyes. Why do we have the eyes we have? Because the components were there. Okay, you gotta work with what you have, right? Other possible amino acids may have been too reactive. It could be that some of the amino acids, and we could have even had those at one point in that tree of life that developed, right? And they could have been too reactive, so they kept getting destroyed. So when they got swapped out with another amino acid and, mutations, that one lasted longer and was beneficial, right? Yeah. And you know what? It may be some combination of all those things. Very well could be, right? They're pretty fair hypothesis. I struggle to call it a hypothesis or theory because, again, I don't think I'm not sure how much actual testing you can do and disproving of it you can do. But we'll kind of go with that. You get the idea. So this is the undesirable reactivity in amino acids. This is homoserine. Can react to produce this right here. This right here is serine. Notice the serine does not perform the same reaction. Okay? Peptide bond or amide bond formation is going to involve these factors. We'll have the linking of the alpha carboxyl group of one amino acids. Everybody remembers the alpha designations and how they work for naming. So the carboxyl group is right here, right? Okay. And it includes this carbon. It's called alpha because that's the carbon it's attached to. Okay? So it's attached to the alpha carbon. So alpha carboxyl. Okay. The alpha carboxyl group of one amino acid is going to be linked to the amine group of another amino acid. This is referred to as a peptide bond by the biochemistry, biology people, but what is it actually? It's an amide, right? It's also a mid-linkage. You could call it that. That's fine. Okay. But anyways, peptide bond, peptide linkage. Biology people will know what you're talking about better if you do that, okay? And the reason that it's referred to as a peptide bond is because it's the linkage between the different monomers of a peptide, right? Anybody know what a peptide is? Yes, the sequence of amino acids, when it gets folded up and incorporated, it would then be a protein, right? Okay, we are going to have the loss of water, and so that is a dehydration reaction, isn't it? And in fact, this is also a dehydration polymerization, isn't it? From back in organic chemistry. Okay? And yes, yeah, it is. That's, I think I even linked it at that time, didn't I? Okay? So does anybody have any questions so far on that? Fantastic. Okay, so polypeptide chains. So we got peptide bonds right here, joining the monomers, peptides, and a polypeptide chain is going to be the chain of the amino acids we refer to as a polypeptide, right? Okay, so each residue, these are referred to as residues, typically in biology, is each amino acid unit in a polypeptide. The polypeptide chains do have directionality because its ends are different. One end will have the alpha amino group, and that's what we refer to as the beginning normally. Okay? Why do we refer to it at the beginning? Mostly because of biochemical designations, like when we actually make the polypeptides. But there you go. Also, it's kind of clever, and it's kind of amazing to me that they actually did a good job keeping the naming in the same direction for all of these things. Like amino acid, and what's the beginning of an amino acid? An amine. Yeah. And then that is the beginning in the synthesis of them, and that is the, like, it stays consistent through the whole chain. Okay? Which is actually kind of amazing. The alpha carboxyl group is at the end, and that's what's considered the ending of it. Okay? Sometimes you see these referred to as the A beginning, C ending. Okay? Polypeptide directionality again, where we have here the beginning. And so the first amino acid in this polypeptide is tyrosine. And then the next one, and you see as we go down. And again, why is that? Because this one has an exposed amino terminal residue, right? None of these other ones have their amines exposed. Okay? This right here then has an exposed carboxyl terminal residue, doesn't it? There you go. Okay. How do you determine the charge on a polypeptide, by the way? Or what determines the charge? Yeah, it's the side chains. Yeah. These always cancel out at physiological pH. Okay? So you always have a Zwitter ion going on here for the chain. Positive on this end, negative on that end. Okay? Okay, so that's the polypeptide backbone. The polypeptide will consist of a repeating part that we call the main chain or backbone. They're used pretty much interchangeably. I like backbone usually. A variable part consisting of the distinctive amino acid side chains. These are the amino acid side chains over here. Notice they're the ones bonded to the carbons. They can face either direction, any direction really, because they're single bonds here, meaning they can freely rotate. Okay? Though there are incentives to lining up in certain directions due to steric hindrances. The backbone has hydrogen bonding potential. Your carbonyl groups are actually good hydrogen bond acceptors. We may have noticed these carbonyls right here. Okay. The NH groups, good hydrogen bond donators. groups, and you can see that right here, right? Fantastic. So again, this is a polypeptide chain. Notice oftentimes when we talk about the backbone of that polypeptide chain, we reduce the side chains to R groups. And so they're just referred to as R1 to R2, R3, etc. Okay? What gives you your numbering here? R1, 2, 3, 4. Yeah. Exactly. Yeah. Yeah. It's which unit it is, right? So which monomer it is. And we start with the amine, we end with the carboxyl. Okay? Notice because of how things typically are going to line up, that this right here is a trigonal planar structure, isn't it? Okay? Everybody see that okay? Okay. The rest of these are tetrahedrals. This is a tetrahedral because it's a lone pair, right? Tetrahedral. Okay? And so what that gives you is it actually gives you right here a plane in which you can orient. Okay? And so by definition, this oxygen and this hydrogen typically have to be essentially anti to each other. Okay? Not perfectly. They don't have to be exactly 100 degrees. They can twist a little, but pretty close. Okay? And what that means is because it's anti to each other every time, the amino acids end up anti to each other all the time, right? So you get up, down, or another way of saying that is in, out, right? And look at what happens to the side chains then. The side chains always end up as this one's out towards us, this one's in away from us, alternating, don't they? Okay? Now, that does mean that we actually reduce the, if we have bulky side chains, we're reducing the interference between these two side chains. So that is kind of an interesting, lucky result of that. But it also means that we don't end up with like disulfide bridges and stuff right next to each other. Okay? All right, so the most natural polypeptide chains consist of 50 to 2,000 amino acid residues. Oligopeptides, another way of saying that is just peptides, is a polypeptide chain made of small numbers of amino acids. Okay? So typically we refer to the peptides as units of like 2, 3, 4 small numbers. Okay? And we would refer to, and those can be referred to as oligopeptides if you want to be very specific. Okay? Where does oligo come from? Anybody ever heard of like an oligarchy? Yeah, that. Yeah, it's the same term. Okay. Small number peptide, literally. I know. Keep that in mind when you're thinking of like the weights of these things and how much van der Waals forces and stuff are going to happen. When we're saying polypeptide, which isn't even usually a whole protein, right? We're talking like 50 to 2,000 units, okay, of amino acids. And those amino acids have an amino, carboxyl, all that with a side chain. So we're not talking about a small number of atoms, are we? No. We're usually talking about tens of thousands of atoms, okay? So the mean molecular mass for an amino acid is approximately 110 grams per mole. This is a very ballpark number, by the way. But they use that quite a bit because when you're talking about large numbers, average numbers, mean numbers work quite nicely, actually. Okay? If you talk about like 10 amino acids, average numbers would work poorly, right? You talk about like 1,000, starts working. So the protein molecular mass can also be referred to in daltons. So a dalton is going to equal 1 atomic mass unit. Anybody remember what an atomic mass unit is? AMU, yeah. And that's the same thing as up here. The AMUs, due to Avogadro's number, have been set to be the same thing as a grams per mole, right? That's why the Avogadro's number is this really weird number, right? Okay, why they use Dalton? Fucking biologists, I blame them. Honestly, is there any damn reason to use a Dalton, which is just one AMU? No, not really, right? Whatever. So right here we see disulfide bonds, which I've referenced several times now, and we can finally see. Yay! So this is going to be a cross-link that's near a cross-linking a linear polypeptide chain. They're formed by the oxidation of a pair of cysteine residues. The cysteine residues have the sulfides on them, or hydrogen sulfides on them, I should say, or thiols, if you will. The cysteines, or two linked cysteines, will be called cysteine. Okay? And so that's cysteine. It's two linked cysteines. Because now it's one molecule, right? So it's a covalent bond. Okay? Notice that it is an oxidation, and that oxidation is going to lose 2 protons and 2 electrons. Okay? In biology and biochemistry, oftentimes you can represent oxidations by either gaining oxygens or losing hydrogens. Okay? And so if you see you lose hydrogens, then that is an oxidation, right? You see that we lost 2 of these hydrogens here. If you gain 2 hydrogens, this would then be a reduction, right? Which is the reverse. Okay. Please note, in biochemistry, almost all the time, you're never going to lose H2, right? Like, that would be the way that organic chemistry would have done this. We would have, like, lost hydrogen gas, right? Or we would have had something to accept these. In biochemistry, we're going to ignore whatever that oxidizing agent that actually does this process is, or the reducing agent that does this process, okay? And that's because there's only really kind of a set small amount of them, okay? Like FADH2 or NADH, okay? And those will always be indicated because they'll come along with the enzyme that's doing the reaction. And so when we look at these reactions, we're going to see it like this a lot. And recognize that these are probably going on like an NAD plus or something, okay? And that's what's transporting these electrons. This electron isn't like jumping off on electricity or something. And the H plus typically doesn't just go as H plus in the solution, though there are a few times it will, okay? But they're very rare. Does that make sense? Don't get fooled by the reactions. Most biochemistry reactions, we just don't mention part of the reaction. Okay. Okay, so this is actually the amino acid sequence of insulin. This was done in 1953. Frederick Sanger actually determined the amino acid sequence of insulin, which is a protein hormone. Everybody's probably familiar with insulin, I imagine. This is a landmark in biochemistry for showing a protein. It has a precisely defined amino acid sequence. This consists of only the L amino acids. They're linked by peptide bonds. It has an A and B chain. So notice it has 2 polypeptides linked together by disulfide bridges. Everybody see that okay? Okay. All right. And note that there's 2 disulfide bridges linking these 2 subunits together, but there is also another disulfide bridge here that changes the structure of this first polypeptide. See it? It's involved in folding it. By the way, is this straight chain? Is this at all what it probably looks like? No, you can tell it doesn't look like that, right? Because see how stretched out that is? Those are definitely being pulled together, right? it's not stretched out. So knowing the amino acid sequence is important, though it is not the whole story, okay? Never fool yourself into that. It is important, though, because the knowledge of the sequence of the protein is usually essential in elucidating its function. Please don't get stuck on that word elucidating. Every now and then I get students, and like from now on, they'll say elucidating. The amino acid sequence determines the three-dimensional structures of those proteins. That's why does it fold the way it does? Well, the primary structure is heavily involved in determining that, right? But you actually do need the folding to determine the function. Or another way of saying that is they all add up together. The alterations in the amino acid sequence can lead to abnormal protein function in diseases, which would be abnormal protein functions. The protein sequence reveals a lot about its evolutionary history. Like we had talked about, you can actually, to a degree, determine the length of time that you'd have between two different organisms in their evolutionary history and how closely they would be related then, okay? By determining how many mutations would have occurred. So these peptide bonds are planar, as I discussed before. This is a trigonal planar structure here due to this carbonyl, right? See that? Okay. It's an sp2 trigonal planar carbon, isn't it? Okay. And so there are 6 atoms that are involved in this planar structure here. There's the alpha carbon. There's the carbon that's in the carboxylic acid right here. So this is the alpha carbon, carboxylic acid here. There's the oxygen, which is in the carbonyl. There's the nitrogen, the hydrogen that comes off of the nitrogen, and finally the alpha carbon on the other one. Second alpha carbon. Does that make sense? Fantastic. These all lie within a plane. Okay? So how proteins actually end up looking is basically slightly twisted and offset planes to each other. Okay? With side chains jutting out of them. Okay? Can you see the side chains jutting out of the plane? Right. And note that this then would be its own plane, joined at the corners, and they'd be offset from each other. Okay? That making some sense? Fantastic. Okay, so the peptide bond has a partial double bond character because of resonance. The rotation around the bond is prohibited. Remember, this is an amide, right? Everybody remembers the amides? Okay. So amides had that rearrangement possibility and that resonance structure. Okay? And this is what creates that very planar structure around there. It's not just that it's a carbonyl, it's that it's an amide. Okay? So the carbon-nitrogen distance around here, this peptide bond, is only 1.32 between the values that are expected for a CN bond, which would be 1.49, and a CN double bond, which is 1.27. You can see it's basically a 1.5 bond, right, in terms of distance. Okay? And we can actually see here the different resonance structures. Remember, the resonance structures would show you the overall structure by combining those two structures, right, into a complete whole. And so here we have the carbonyl with the double bond on it, and these electrons can actually flow over into this, creating some double bond character. This is represented by this resonance structure here. Okay? Another way of thinking of this is this has a p orbital, which has a pair of electrons here on this nitrogen that can form a resonance structure with this, right? Or another way of saying this is a very electronegative atom, and so can pull some of those electrons in that double bond. Okay? Anybody have any issues with this? Did I lose anybody here? I know, this is the organic, right? Paid off, all that studying and effort. Okay, so in our trans configuration, the two alpha atoms are on opposite sides of the peptide bond. You can actually see the peptide bond right here. These are the alpha atoms, see that? And that's what I was talking about when I said they're up, down, right? So they're on opposite sides, they're anti to each other. Or another way of referring to anti would be trans, right? Okay. And trans is actually properly used here because this has double bond character. And so you can refer to this as a trans configuration because it is restricted. The steric repulsion between the groups attached to the alpha carbons actually will hinder the formation of your cis configuration. And this is why we don't see the cis configuration. So theoretically, even though this has some double bond character, right, we could have assembled it in such a way that they're on the same sides, right? Which would be this. The alpha carbons are on the same sides. But the problem with that is there's already a little bit of an energy barrier for these carbons here, but amino acids don't just have hydrogens usually on these, right? If we had two glycines, the energy barrier wouldn't be huge. But what would happen if we had tryptophans? That's a huge group, right? Yeah, so there is some steric repulsion for things like glycine and stuff, but some of these amino acids would have just astronomical steric repulsion for having these near each other. So proline actually has a unique geometry, and that's because proline is that one that wraps back in. Remember that? So it wraps back in and bonds that nitrogen again. Okay? And so when proline follows another amino acid, the steric differences between the trans and cis forms are actually minimal. And so what will happen with proline is we'll actually get both forms because there's no significant difference between the two. Okay? And so we'll end up trapped in one of these two forms, mostly trapped in one of these two forms of trans and cis for proline. And so what do you think proline has a tendency to show up in? Structures that would result from a cis, right? If you need to wrap back around in a cis configuration to form some sort of structure, guess what's going to show up? Proline. Because it's one of the few that you could actually do something like that, right? That there's not this huge energy difference between cis and trans. All the other ones, trans is so much more stable, you're not going to form cis. You can't fold that way. Okay? Okay, so click on a peptide bond here. Which one would be a peptide bond? There's some options.
In between the C that's bonded to the bond.
You got it. Yep, you got it. Peptide bonds. Okay, so torsional angles, or another way of referring to torsional angles, is dihedral angles. This is the rotation about the CN bond. We can refer to that as phi. That's the symbol for phi, by the way. And the alpha carbonyl carbon bond, which we can refer to as psi. And that's actually the symbol for psi, by the way. This determines the path of the polypeptide chain. Not all torsional angles are permitted because of steric collisions between the atoms. As we had discussed before, very large ones can cause steric hindrance, and we can have various different slight bends there. Okay? Remember where I was talking about that offset of the planes? That's essentially what this is. Okay? It's the offset angle between those two planes. So this right here is these angles. Okay? Okay, remember that we have phi and psi. Okay? So this is the angle around the nitrogen and alpha carbon. Okay? Nitrogen and alpha carbon right there. Is that making sense? If we look at these, what we do is we line up a plane, we take that bond to the next one, so the nitrogen alpha carbon bond, we look at how much it's offset off of that plane. And then we would measure the angle. Can everybody see my sort of hand figure? Or look at this figure and go, okay. So this is the plane, see that? And then this is the bond offset off of there. Okay? Okay. And this is the point around which you have free change. Okay? Because this is both the beginning and ending point right here for both of these planes, aren't it? It's the one you end at for one and begin at for the next one. Okay? So it dictates where that plane is. All right. This right here then is the psi, And this one's over here. This is the alpha carbon going over here to the carbonyl. Okay? And can you see that's that next plane there? Okay. That making sense so far? These are the ones that ultimately determine what's going to happen. Are you making a helix? Are you making a sheet? What are you doing? Okay? These numbers added together along that string will determine the structure, right? Okay, so Ramachandra, okay, I'm going to be honest. I am terrible at certain languages. So names, Indian people's names, I'm really bad at, actually. It's sad because I worked with the majority of Indian people in grad school, and I just am really bad. Sorry. I'm actually better at Chinese names, but... so anyways, Ramachandran plot. Somebody can correct me if they have it better. No? Okay. This illustrates the phi and psi angles that are allowed. 3/4 of the possible phi and psi combination are actually excluded by local steric clashes. So for example, this right here is disfavored because it would bring these two groups too closely together and they would have a steric hindrance clash, right? Okay. And see, all this is it's just a phi versus psi angles. Okay? Can anybody tell me why the max is 180, minimum is negative 180? Yeah. Basically, after that, you just repeat, right? So, like saying positive 0 to a positive 180, you can actually just go the opposite direction. It just repeats, right? These. Yeah. And the darker it is, the more favored. Okay? And so the majority of states are going to be these ones here, this dark patch here, and this dark patch here. Okay? You can have these other ones, but these lighter patches are going to typically happen if you have something driving them. You'll have to have like a disulfide bridge linking stuff to squeeze it a bit, right? Because it's slightly disfavored. Does that make sense? It's less energetically favorable. And then the white stuff is just, it's not happening, okay? Please note that this sort of curves in like this, and it should look like that, right? If you went over this, right, like that. See that? On the bottom here? Yeah. This is just up here, because we wrapped back around, haven't we? Okay, does anybody have any questions about any of this so far? Okay, fantastic. Okay, so the secondary structure equals the three-dimensional structure formed by the hydrogen bonds between peptide NH and CO groups of the amino acids. They're near one another in the linear sequence. So some of the examples of secondary structure are going to be alpha helices, beta pleated sheets, and turns. These are the primary secondary structures. There is some proposed other secondary structures I've heard of before, though I don't think they have been approved, as it were, or widely utilized. Another way of saying. You can think of these a bit like the motifs, the repeated patterns you see within these proteins. Okay? Okay. Now, again, they're going to be what results from the stuff we've already talked about, aren't they? Why do they happen? They happen because we have these allowed angles, right? And they're twisting so that the hydrogen bonds can occur to the ones that come close to each other. Okay? Without the side chains having significant steric interference. Okay? So all of those things build up to give you the secondary structures. Right? And the secondary structures are then going to build up further, but we need to talk about secondary structures first. Let's not get ahead of ourselves. The alpha helix, by the way, I will try to make connections as I go along. But I can't make all the connections for you all. I'm sorry. You're going to see in here that, like, you're going to look back and you'll spontaneously start making connections if you really got this. Okay? And some of them you won't make, and then you may be like 20 years from now in a career in biochemistry, medical, whatever, and you make that connection and you go, oh, shit. It's so much. Anyways, the alpha helix, this is a tightly coiled rod-like structure. Yes, it is a helice. It does not have any like empty space in it. This is very commonly mistaken and not understood, and people think it's like an empty tube. It's not. It's basically filled in. Okay, there's not really a lot of gap inside. Okay, so it's more like a rod-like structure, a bit like a ram's horn or something. You know how those twist? Yeah. You guys have all seen the, or I guess unicorn horn would probably be the better example, wouldn't it? The unicorn horn that you always see on mythical unicorns, twisted structure, filled in, rod. Yeah. So with the R groups are going to be extended outward within a helical array. So the R groups are going to be jutting outwards at offsets to each other as you go up. Does that make sense? A bit like thorns off of a rose. Okay? Just more structured. So all of the backbone CO and NH groups from the hydrogen bonds, except for those near the ends of the alpha helix. So all of these carbonyl acceptors, hydrogen donators, will form hydrogen bonds within an alpha helix. Okay? They'll all be used up, except for the ends, of course, because we stop. Okay? The CO group of each amino acid forms a hydrogen bond with the NH group of the amino acid that is situated 4 residues ahead in the sequence. And so what we'll see is we'll have an N+4 pattern. Okay? Okay. And this actually will demonstrate it much better. And this is, by the way, this is the reason your book is awesome. Okay? You may have noticed the references in some of the tables for actual publications, right? Which is already pretty cool. That's neat. But these figures are amazing in your book. It's a great figure, and I've never seen any other biochemistry book that has this level of figures. Okay? So what is this? This is what an alpha helix looks like in abstractia, right? And these are the side chains coming off of it, and as you can see, they jut out at nice little offsets to each other, right? And it overall looks a bit like a coiled ribbon or something, right? So a helice. Now, you can't really see these helices in the actual structures when you look at them. It's hard to see, right? But you can see the R groups and how they match up, can't you? Which is nice. Okay? Really cool, right? Because it matches perfectly. Somebody put in some serious effort. Okay, so these are the nitrogens right here, the hydrogen bond donators, right? And we see as we curl around, each of them is hydrogen bonded, isn't it? To the 4 offset residue carbonyl. And if you count, you'll actually see 1, 2, okay, we'll count the options. 1, 2, 3, 4. See that? So it's a 4 offset. And that is what's referred to as periodicity, okay? It's the period at which it repeats the pattern. See that? And so it takes 4 amino acids to curve back around on the same side, okay? And that's how these R groups are offset, okay? And so if you took the average angle, you could divide 360 by 4, and you'd figure out the average angle of an offset for an R group, wouldn't you? I know. You see all the connections you can make and other information that's being provided. I'm going to try to point some of this out, but I can't get everything. Time's going to be limited, right? This is actually looking down the structure. And so, yes, there is theoretically so if you look at it as a ball and stick model, it looks like there's like a hollow, right? But remember, ball and stick models are bullshit. Okay? In reality, these have space that's filled in with the electron density, right? With charge. And so this is what it actually looks like. And there's no hollow. You're not fitting anything in that. Okay? Light can maybe fit in, but that's it. And it's going to get interfered with. Does anybody have any questions? You can even see the twist and twirl on the space filling model and everything else. The offset there. And this is the R groups coming along. And notice how it's almost like a porcupine look. Instead of being like right angles offset, it's at an angle because it's tetrahedral, right? Can you see that? Ooh, that's beautiful. Okay. Anybody have any questions about any of that? No? Okay. Okay, so did I say n plus 4? Yeah. Okay. So, So right here is the carbonyl that's going to hydrogen bond to this one right here, right? Okay. So this right here would be I. So this is the residue I. Meaning if this is 1, this one's 2, 3, 4, 5, right? Does that make sense? Okay. And so what you're going to see here is that the carbonyl on this is going to be hydrogen bonded to the one that's 1, 2, 3, 4 down. Okay? I'm glad I actually did find them. Because I wasn't really thinking about it when I said it, and it just sort of came out. I don't even remember what I said. Anyways, so what if this was 10? Which one does hydrogen bond to? So this would be 10. It hydrogen bonds to 14. Okay? 7? 11. You got it. And that's how that works. Okay? And that's the periodicity. And that would be where you'd start seeing the R group lines up with each other. Okay? Note that's enough distance that they have very little impact on each other. So the residues are going to be separated by a rise or a translation of about 1.5 angstroms along the helix axis and a 100-degree rotation. Okay? An alpha helix contains 3.6 amino acid residues per turn. So recognize that this is not a perfect offset. Okay? It's not exactly 4 gives you the exact offset and now they're aligned. And in fact, you can actually kind of see this in the figure if you look very closely. See how it's not at perfect offsets, they're a little bit off. Yeah. Like they don't perfectly repeat, do they? So it's actually 3.6 amino acid residues per turn. The hydrogen bonding happens at a slight angle, but the hydrogen bonding oftentimes does, right? Because are you actually connecting the hydrogen here and this parallel right here? Not normally, right? Yeah, it's the orbital right here, the charge, right, that you're connecting with. Okay. So the pitch is equal to the length of one complete turn along the helix axes. Okay. This is equal to the product of your rise and the number of residues per turn. So what are we talking about? Well, one rise would be this difference here. Okay? So if we just look at the vertical distance, that's 1.5. Okay? And then we have a repeat every 3.6. So we go up 1, 2, 3, 6, up here. And that's going to be 3.6 times 1.5, 5.4 angstroms distance. Okay? Does that make more sense? Okay. Fantastic. Am I out of time? Okay. Ooh, yeah, I'm gonna have to take a knife to my